the second part of the session. So our first talk will be from Guennadi. I see Guennadi connected. Can you please share your slides?
Hello. Yes.
Hello.
I hope you can hear me.
Hear you well.
And now I hope you see my slides, right?
It's a bit slow for me, so maybe other people can see them.
Yeah, we can see the slides.
Yeah, it's working. Thank you. Thanks.
Okay, so I can start. So I will present the results of ATLAS experiment on the measurement of the W branching fractions, which we obtained from the decays of top quark. And the main goal of our measurement is to test lepton flavor universality. In the standard model, the coupling of all charged leptons with W boson is expected to be the same. And this assumption is fundamental for the standard model. It's not proven by any theoretical theorem, but still it is a cornerstone of the standard model, and it is known as lepton flavor universality. So in the standard model, the only difference between the leptons is due to their mass. And more precisely, the coupling of leptons to the Higgs bosons is different. And it is actually verified recently experimentally, as it is shown in my plot to the right. Lepton flavor universality tested at low energy with very high precision. More precisely, it is tested in the decays of tau leptons, and scientists measure the coupling constants of different leptons to W boson. As you can see from the numbers shown in my page, the precision of this test is at the level of 1 per mil, and all results at low energy agree very well with standard model. So the coupling constants are essentially the same. The same lepton flavor universality is also tested in W decays, directly in W decays to different leptons and neutrinos. And these measurements are performed at lab and at LHC. Here, the precision is not so great. It's at about 0.8% for the ratio of branching decay width of W to mu nu and W to E nu, as it is shown in my slide. And it is at the precision is at the level of 2.4% for the ratios of decay of W to tau. Also, as you can see from the plot to the right and also from the numbers, there is a mild tension with the standard model in the decays of W to tau lepton. So it is at the level of 2.7 sigma, and it mainly comes from lab results. So, but of course, this tension is quite interesting, and it prompts to perform additional tests of lepton flavor universality. So more precisely, it's very interesting to measure the ratio of partial widths of decay of W to tau nu and W to mu nu, as it is shown in my slide. So if we succeed to measure this ratio with the precision of about 1%, and we obtain the mean value of this result to be the same as at lab, it would be a definitive confirmation of lepton flavor universality violation. So, and by itself, it would be an unambiguous discovery of physics beyond the standard model. So this test is very interesting and important, and that's why we want to measure it. But of course, measuring the ratio of branching fraction of W to tau and W to mu is quite difficult, and especially when we consider the work at hadron colliders. And for a long time, it was thought that this level of the precision at the level of 1% is impossible to achieve at hadron colliders because of large background, large uncertainties, and so on. But the new atlas result, which I will present today, disproves this belief. So what is the analysis strategy? We test lepton flavor universality using decays of top quark. Top quark is produced, the cross-section of top quark production is huge at relatively huge at LHC. As you can see, this point is at the level, so the cross-section is at the level of about 800 picobarn. So it means that already now we have about 100 million ttbar pairs. And also selection of ttbar is relatively simple and clean. Each top quark decays to a W and B quark. So in each event of ttbar production, there are 2 W bosons. And because of this, our analysis method is so-called tag and probe method. We use one W boson just to select events, ttbar events. And we use the second W boson to measure the ratio of branching fraction of W to tau and W to mu. And I denote it in my talk using this notation, RT mu. More precisely, we use the decay of tau to muon and neutrinos, and we measure the ratio as it is shown in my page. Because, first of all, we know the branching fraction of decay of tau to mu and neutrinos with reasonably good precision. And what is important with this selection, in the final state for both decay modes of W, we have the same single particle, the same, it is a muon. And when we take the ratio of such events, many uncertainties cancel, like uncertainty of jet reconstruction, flavor tagging uncertainties, and so on. Uncertainties related to the selection of tag W boson. And because of this, we hope to achieve a high precision of our measurements. The selection of events of ttbar is straightforward, and it is more or less standard. So we select the decays of top quark, semi-leptonic decays of top quark. So top quark decays to lepton, neutrino, and B. We require 2 isolated opposite charge leptons, mu or mu pairs. And the tag lepton can be electron or muon, and it is selected with a single lepton trigger. On the contrary, for the probe lepton, it must be a muon, and we essentially just apply the cut-on transverse momentum of this muon greater than 5 GeV. Otherwise, we don't put any condition on this probe lepton. We require 2 B-target jets in the events because of this big quark from top quark decay. And for mu events, we apply as a 0 beta. So we require that the mass of 2 muons is, we remove events when the mass of 2 muons in this limit, just to remove the Z0 contribution. And with this very simple and straightforward selections, the background is quite small in mu sample. It is at the level of 0.9% only. And it is higher in mu sample because of the Drell-Yan contribution. But we can control this contribution of this background. The main quantity which we use to select the decays of W to tau and mu is a muon impact parameter. And schematically, the definition of this quantity is shown in my sketch in this page. So it is a distance of closest approach of a charged track to the beam line in the transverse plane. So in the plane which is transverse to the direction of the beam. This impact parameter is 0 for particles produced in the primary vertex or in the primary interaction point. However, tau lepton lives quite a long time, so it decays at a distance from the primary interaction. And that's why it has a non-zero, the muon produced from tau decays has a non-zero impact parameter. Now we need to separate two decays of W, decays to tau and decay to mu. And we separate these decays using two variables. It's one of them is muon impact parameter, which I described in the previous page. And another variable is muon transverse momentum. And muons which come from the decay of tau lepton, they on average have a smaller transverse momentum just because a part of the energy of tau is taken by invisible neutrino. So if we look on the schematical distribution of these two quantities for muons which come from tau or muons which come from prompt muons, on average, muons from tau have larger impact parameter and smaller transverse momentum. And we exploit these differences to separate two decay channels of W. So we perform a two-dimensional fit of the probe muon impact parameter and PT. What are the sources of muons in our sample? Of course, the main source is prompt muons which come from the decay of top quark, top to mu B. So on the plots to the right, you see that it is the largest contribution. It dominates at small impact parameter and large transverse momentums. The second contribution comes from muons from which come from the decay of tau lepton. So when top quark decays to tau nu B, and tau decays to muon. And you see from my plots to the right that this contribution dominates at large muon impact parameter. It's the lower plot, and it has small transverse momentums. There are also some background contributions to our sample. It's muons which come from hadron decays and muons from decays of Z to mu and Z to tau tau. The fractions of prompt muons and muons from tau decays are floating parameters in the fit. But the fraction of the contribution of Z to mu and Z to tau tau is measured in data using a separate measurement. And the fraction of muons from hadron decay is estimated using data with some input from Monte Carlo. As I said to you, we perform a two-dimensional fit of using a profile likelihood method. So we define 3 bins in muon PT and 8 bins in muon impact parameter, in absolute value of muon impact parameter. And we have 2 channels. We fit all of this simultaneously. So we have 48 bins in total. There are 2 free parameters in the fit. It's a constant scaling factor applying to muons, prompt muons from top quark decay and muons from which come from tau decay. And it is just a general normalization of our events. And also we apply the quantity parameter of interest is RT mu. It's the ratio of W decay to tau, branching fraction of W decay to tau and W decay to mu. And of course, we apply this ratio, this factor only to muons which come from tau decay. In this page, I show the comparison of the data in Monte Carlo after our fit. So there are 3 plots here which correspond to different PT bins of muon. So it's a lower PT bin, the PT of muon between 10 and 20 GeV and more than 20 GeV. And you can see that the distributions are the distribution of the muon impact parameter. And you can see that in all cases, agreement between data and Monte Carlo is reasonably good. So these 3 plots are for the sample with electron and muon, so tag electron and probe muon. And on the next page, I show the same plots for the comparison of mu sample when we have tag muon and probe muon. But what I want to demonstrate is that in all cases, we have a very good description of our data using our input from Monte Carlo. And here is our result. So the measured value of this ratio of branching fraction of W to tau and W to mu is equal to this number. And you can see that it is consistent with standard model with the uncertainties. But what we're really glad to present that our uncertainty is now at the level of about 1.2%. And unfortunately, we don't see, fortunately or unfortunately, it depends, but we don't see any deviation from the standard model expectation. So this ratio in our case is equal to 1. So we don't agree to the lab results, as it is shown on my plot below. So this is our point here, and this is the previous lab measurement. So our point is consistent with the standard model. So here I just mentioned very briefly about the uncertainties. The systematic uncertainty is dominating in our case, and the main contribution comes from the description of muon impact parameter. There is also a contribution from modeling of ttbar, modeling of muons which come from hadron decay, and muon reconstruction and identification. And of course, more results are, or more details are given in our paper, which is already available. So I come to the conclusion. Atlas experiment developed a new technique of the measurement of this, of the test of lepton flavor universality, and huge statistics collected in round 2 allowed us to measure the ratio of branching fraction of W to tau and W to mu with very high precision. It is the world best precision so far. Our result resolved the old discrepancy with the standard model, which remained from the lab era, but regretfully, we have a beautiful confirmation of the standard model. That's all. Thank you very much.
Thank you very much, Guennadi, for your very nice and clear talk. So for questions, please, if you raise your hand, or if you can go ahead directly. Okay, I don't see any raised hands. So I have a small question concerning the dominant systematic uncertainty, which I see is due to the D0 tail modeling as you've described briefly. But just if you can say a bit in a few words more about this and how you can see it as improved in the next iteration.
Yeah, so for this uncertainty, it depends on the available statistics. So we estimate this uncertainty using data, and we correct our description of muon impact parameter using data. More precisely, we correct it using the decays of Z0 to mu plus mu minus. And of course, with the increase of the statistics, we can do more accurate estimate of this templates of muon impact parameter, and hopefully with more statistics, this uncertainty can be decreased.
I see. Thank you very much. Okay, so I don't see any other questions. So thank you very much, Guennadi, for your talk. And I think we can move on to Giacomo. Giacomo, can you
Hello,
hear
can you
us?
hear me?
Yes, yes, we can hear you. Can you please share your slides?
Sure. Can you see the slides?
Not yet for me. Yeah, it's okay. You have 15 minutes. Thank you very much.
Okay. Hello, I'm Giacomo, and on behalf of the CMS collaboration, I will present the recent results on vector boson plus jet measurements, namely differential cross-section measurement of the Z over gamma ratio and the study for collinear Z boson emission. with the large statistics collected in the run 2 V plus jet measurements, give the opportunity to perform precision tests of the standard model in extreme region of the phase space that were previously limited. And thanks to the versatility of V plus jet processes, they can be used to probe different aspects of the standard model as perturbative QCD effects, higher order correction from QCD and Electroweak. They are important input for determining the PDFs. And on top of that, they improve the sensitivity of searches for new physics and measurements. For all these reasons, there is an active theoretical development with the latest calculation providing NLO QCD and NLO Electroweak precision. And theorists need experimental measurements to validate their predictions. And the plots that I include in slides gives a nice overview of the efforts that has been carried out by CMS during run 1 and run 2, and gives you really the idea of the amount of work and the number of results that has been already published. Today, I will focus about the Z over gamma ratio and the study for collinear Z-boson emission. And these results have been recently published in one paper. And they are the first measurement of differential cross-section ratio for the Z over gamma at 13 TeV, and the first explicit study for collinear Z-boson emission from a jet at the LHC. So starting from the ratio analysis, this variable is of particular interest because it's sensitive to higher order QCD and Electroweak corrections. And while QCD corrections are mainly flat versus the PT of the vector boson, Electroweak corrections grows with the PT, as is described by the plot in slides, due to the large Electroweak Sudakov logarithms. And on top of that, this analysis is relevant to BSM searches that target missing transverse energy in the final state, as the Z plus jet and the gamma plus jet samples are used to model the Z2 neutrinos background. And these searches looks more or less like the one that I reported in slide. So here the signal that you're trying to find is the blue dashed line, and will manifest itself as a small excess of events in the very high tail of the missing transverse energy distribution. So you really need the precise modeling of the boson PT at high energy. So the event selection for this analysis is reported in slide, has been carried out on the 2016 CMS dataset using the single muon and single photon samples for the Z2 muon and the photon channel respectively. In particular for the Z plus jet channel, we require 2 well-reconstructed muons with a PT above 30 GeV and an absolute rapidity less than 0.4. They need to have opposite charge, of course, and they need to be, the environment mass need to be within 20 GeV of the Z mass peak. On top of that, the dimuon per PT needs to be above 200 GeV and the absolute rapidity less than 1.4. Similar requirements are in place for the gamma plus jet channel. So one well-reconstructed photon with PT above 200 GeV and the same centrality requirement. And in both cases, we require events to present at least one jet in the final state with a PT above 100 GeV. So for the Z numerator of the ratio, so the Z plus jet cross section, here is the out-of-the-box data Monte Carlo comparison. And from this plot, we can learn that the background is at 2.5% level, more or less, and mainly from diboson Electroweak Z plus jet production. And once we subtract this background, we can unfold the reconstructed event yield to the particle level. This is due to this is done to then perform compare our measurement with different predictions, and the unfolding basically aims to invert the matrix that is reported in slide, which is the migration matrix built on simulation, and tells us how the reconstruction process smear the underlying Z PT distribution. Once the result is unfolded, one needs also to take into consideration systematic uncertainty, and the strategy is to repeat the unfolding procedure with alternative migration matrices that are obtained with plus minus 1 sigma sheet variation, one variation per each systematic effect that is considered. And the busy plot that I included in the slides gives you an idea of the different contribution from the different sources. The main take-home messages here are that above 800 GeV, we are statistically limited on the Z plus jet PT measurement, and that the dominant systematics for this measurement are due to the muon scale uncertainty and the uncertainty related with the unfolding procedure. So once we extract the unfolded Z plus jet cross-section differential in PT, we compare it with different theoretical predictions. And here in blue, we have a MATGRAPH NLO prediction. In red, the MATGRAPH leading order, and in orange, the Sherpa plus open loops prediction, which is at next leading order in QCD and the Electroweak. And we can see that the orange, so the Sherpa plus open loop prediction really does a good job in predicting the behavior of the data. So coming on the numerator of the ratio, again, we have the similar data Monte Carlo comparison. And here the largest background is from QCD multi-jet, where electron or pi0 from jets are misidentified as a photon candidates. And since this background is a bit more tricky, we dedicated a data-driven methodology to estimate it and to extract the purity of the photon selection. So the purity is basically as reported in the slide, is the fraction of real photon out of the number of selected events. And it has been measured in different PT bin of the photon, and therefore provides basically a differential measurement of such background. Once we determine this background, we can subtract it and perform, as we did for the Z plus jet, the unfolding procedure. Again, this is the migration matrix for the gamma plus jet PT. And once you invert this matrix, you can look at the unfolded distribution. Of course, you need also to include systematics, and this has been estimated in a similar fashion what has been done for the Z plus jet. Here, the statistical uncertainty is dominating only in the very last PT bin. And as we saw for the Z plus jet, the scale uncertainty on the photon is really the dominant one, as well as the uncertainty on the unfolding. So we have compared the gamma plus jet unfolded cross-section with 4 different theoretical predictions. In blue, we still have the MATGRAPH NLO. In green, we have the JetFox, which is a physical calculation at NLO precision. In orange, we have the Sherpa plus open loops, and in red, the MATGRAPH leading order. You can see how the MATGRAPH NLO is actually the best out of the 4, doing really an incredible job in and describing the behavior of the data, whereas the Sherpa plus open loops, while does an acceptable job in the very high PT range, tends to overshoot the data in the intermediate boson photon PT range, so between 200 and 500 GeV. And this is directly visible when we look at the ratio, because if you look at the 200 to 500 GeV range for the Z over gamma ratio with the orange prediction, so the Sherpa plus open loops prediction, you can really see that the prediction is undershooting the data, and is directly connected with the excess of photons, basically, that the Sherpa plus open loops is predicting. Whereas the MATGRAPH NLO in this region does a good job following the measurements, basically. In the high PT tail, the high PT region, as expected, if you consider also NLO Electroweak corrections, the behavior of the ratio is to decrease more, and we can see clearly here. And also, it can be noticed that the Sherpa seems to be better in fitting the data in this region. So coming to the study for the collinear Z boson emission, if you think at Z plus jet production, a leading order, the topology will be the one depicted in the top box in the slide. So you will have the Z boson recoiling against the jet systems, and the delta R between the Z and the closest jet will be as the one depicted, reported in the top plot. So basically, you will have a distribution that is peaked at pi, so in a back-to-back configuration. But once you consider also NLO Feynman diagrams, as the one that is reported in the box that is on the bottom of the slide, you can have also different topology coming into play. So basically, you can, in this case, you can have a dijet system in which one of the jet is energetic enough to irradiate a Z boson. In this case, you would expect that the delta R between the Z and the closest jet would be much more close to 0. And in fact, this is what you can see from the 2 plots that are included in the slide. So the strategy of the analysis is to try to enhance this sort of contribution compared to the back-to-back configuration, basically. And to achieve that, it turns out that you can simply apply a very hard threshold on the LeadJet PT. And the two bottom plots are the delta distribution for two different thresholds. So at 300 GeV or 500 GeV on the LeadJet PT. And you can see that the higher you go on the threshold for the LeadJet PT, and the more the collinear region is enhanced with respect to the back-to-back configuration. So the selection for this analysis mimics the selection that has been implemented for a Z plus jet channel. So we have the same requirements on the muon, but of course, we changed the requirement on the LeadJet PT. So we asked for 300 on 500 GeV on the LeadJet of events. Also, we dropped the 200 GeV cut on the ZPT, of course, and we don't cut on the Z rapidity. And as I said before, the variable of interest is the delta between the Z and the closest jet. And to have an idea of what Electroweak correction may do to this distribution, here included a theoretical prediction where you can see that basically the whole distribution is sort of affected. Not only the collinear region will change, but also the back-to-back peak should change with the Electroweak effects. So then the analysis follows really a similar strategy to what has been done before. We unfold the reconstructed event yield to particle level, and this is the migration matrix for the delta R for the 300 GeV selection. Systematics are estimated again in a very similar way, and this is even easier as a plot. But basically, what I want to say from here is that again the dominant systematics are due to the muon scale uncertainty and the unfolding procedure, and especially in the low and very high delta region, the dominant uncertainty is due to the unfolding, and specifically due to the statistical uncertainty on the unfolding matrix. So now we can compare the unfolded cross-section with the different theoretical predictions. And here we have in blue the MATGRAPH NLO predictions, in red the MATGRAPH leading order predictions, and in orange the Sherpa plus open loops prediction. And if we look at the left-hand side, we have the distribution for the 300 GeV threshold. And we can see that the box plot, it seems that the Sherpa plus open loops prediction does a slightly better job in reproducing the full shape of the delta R variable. But if we go to the 500 GeV threshold, the statistical uncertainty on the Sherpa prediction is basically too large, and you cannot really tell anything about it. But another interesting thing is that in the 500 GeV, you can see that the leading order MATGRAPH prediction is performing better than the next leading order prediction. And this might be surprising, but actually, but actually, these two predictions have been different, are a bit different in the sense that the NLO prediction has 2 hard jet in the matrix element calculation, whereas the leading order goes up to 4. And since the delta R variable is really sensitive to the number of jet multiplicity, this might be the reason why the leading order prediction performs better in reproducing the shape of this variable. So this brings me to the conclusion, and I presented the differential cross-section measurement for the Z plus jet, the gamma plus jet, and the ratio, and the study for collinear Z boson emission. And this, as I said in the introduction, made the first measurement of the Z over gamma ratio at 13 TeV, and extend the sensitivity on this variable up to 1.3 TeV in the vector boson PT. And also these are the first study for collinear emission for Z boson from jets at the LHC. And studying regions of the extreme phase space is really becoming increasingly important in the current era of the LHC, where a lot of data are available, and we are probing higher and higher thresholds and exploring new territories. That's all from my side. Thank you.
Thank you very much, Giacomo, for your nice talk. So I see Tanya raised her hand, so please go ahead.
Yeah, can you hear me?
Yes.
Yes, very good. I have a question for slide 15. Yeah, maybe you said it and I didn't listen or didn't get it. Also, I mean, it looks pretty obvious that somehow Sherpa and Metcalfe agree on this one bin above 1 TeV for the PT, and right. You don't, so to say. So, okay, I mean, the first question, I think you didn't plot really the uncertainties which would be associated with the theory prediction, so to say, right? So, I mean,
yeah, the uncertainty is only on the ratio plots here. So, and is only actually for the Metcalfe prediction.
Ah, yeah.
Right. So,
yeah, but I see it. Okay, statistical uncertainty.
Yes.
And theory and statistics. Okay. Okay, I mean, what is the take of this? Are you waiting now for full run 2 data analysis to see whether this goes away, or other detailed investigation?
Yeah. So basically, our take on this particular data point is that we see basically a fluctuation in the data actually, and basically it's not really significant actually. And yes, as I said, this analysis has been done only on 2016 dataset. So the idea is then to perform, and also because the Z plus jet channel is quite limited statistically, starting from 800 GeV. The idea is to then go for a full run 2 results with also include the electron channel, because here is just that muons, and that should be. I mean, that really should help, let's say.
Yeah, okay. So we wait, because I think the theory looks more believable somehow than this dip. I don't know where this should come from, but okay. Okay, thank you.
Thank you, Tanya. So I see also a question from Guennadi.
Can you go to the page 9?
Yes.
There is some disagreement between data and Monte Carlo, which looks to me quite significant. How can you interpret it? And
so basically, as I said, also, I mean, slide 8 is really slide 7, I think. But yeah, basically, this is just out of the box data Monte Carlo comparison. So we are not correcting, applying any scale factor to Monte Carlo yet. It's just to look at the relative contribution. So you don't want.
Okay.
Pay too much attention about data Monte Carlo comparisons here. Also, the other thing is that the gray band that you see in the ratio is just the statistical uncertainty of the Monte Carlo. Sorry. So basically, if you then you will add some the systematic effects, the uncertainty band will be higher. In general, we just want to see here that the number of events is more or less the same, and we are not completely off, basically, just to assess the contribution of the background.
Okay, thank you.
Okay, thank you. There is a question also from Aram.
No, it's actually, I had the more or less the same question as Tanya regarding the Sherpa predictions, so it's okay, thanks. Yeah,
me too. Okay, so thank you very much, Giacomo, for your nice talk. And so we can move on to Aleksandra.
Okay, thank you very much. I will stop
Thank you. Thank you.
Yes, hi, can you hear me? And
yes, we can hear you. Can you please share your slides?
Yes, I'm sharing now. Do you see it?
Yes, it's working now. Thank you. You have also 15 minutes. Thank you.
Okay, thanks a lot. Okay, so today I want to talk about the predictions for Drell-Yan PT obtained with Parton Branching TMDs matched with NLO calculation from MC-ADNO and energies from fixed target to LHC. So I think I don't have to convince anyone in this audience how important the Drell-Yan process is. So it's used as the standard candle for precision measurements at LHC. It helps us to understand QCD evolution, resummation, factorization, both the collinear and transverse momentum dependent one. It's used for the extraction of the PDFs. At low mass and low energies, it gives us the access to Parton's intrinsic momentum. However, the description of the Drell-Yan data in a wide kinematic range is not trivial, it's problematic. So the basic tool to obtain the QCD collider predictions is the collinear factorization theorem, which is schematically written on top of my slide and shown in the picture for Drell-Yan process. It factorizes the cross-section into partonic process, marked with the blue frame, and Parton distribution functions denoted by the blue circle. It works really well for inclusive single scale observables, but it describes the proton structure in longitudinal direction only. So when there are processes which involve more scales, then also the transverse degrees of freedom have to be taken into account. So in other words, the soft gluons need to be resummed. The formalism, which provides the treatment of soft gluon resummation, instead transverse momentum dependent TMD factorization theorem, like low QT Collins-Super-Sterman or high energy KT factorization. However, for practical applications, what we really need is to have a Monte Carlo approach. So today, I want to talk about the Parton branching method, which provides such a Monte Carlo approach, which is based on a TMD factorization theorem. So what Parton branching method is doing, it promotes this formula from the top of the slide to the KTE dependent formula. So we have the transverse momentum dependence in the Partonic process and also in our PDFs, which are now TMD PDFs, what we call TMDs. Parton branching method aims to be applicable in a wide kinematic range for multiple processes, multiple observables, and also it aims in a consistent treatment of transverse momentum during the whole generation of the process. So the Parton branching method contains two key elements. First, it delivers the TMDs in a wide kinematic range from the Parton branching TMD evolution equation. The initial parameters of those TMDs are fitted to HERA data. And then the second key element of the Parton branching method is that it can be used as the input to the TMD Monte Carlo generator to make use of this formula and to obtain predictions for QCD collider observables. So my plan for today is to describe briefly how do we obtain those Parton branching TMDs, then how do we use them to obtain predictions, and then at the end of my talk, I want to show you some results for the Drell-Yan PT spectrum. So the key element of the Parton branching method is the TMD evolution equation, which is written here in this slide. It has a form which is very similar to DGLAP evolution. However, additionally to DGLAP, it contains also the transverse momentum dependence. It has a very easy intuitive interpretation. So when we have a Parton A, at scale mu squared with longitudinal momentum fraction x with transverse momentum kt, we ask where does it come from? So the first term of this equation describes the evolution of Parton A between scale mu 0 and mu without any resolvable branching. The probability of such a process is given by the Sudakov form factor, which is defined here. Then the second long term in this formula describes the scenario where we have a Parton B at scale mu 0. It evolves between scale mu 0 and mu 1 without any resolvable branching, what is given by the Sudakov here. Then at scale mu 1, we have a branching governed by the splitting function. The splitting function gives us the probability that Parton B will split into Parton A, and then Parton A evolves between scale mu 1 and mu without any resolvable branching, what is given by the Sudakov form factor here. Then we have also the scenarios with 2 branchings, 3 branchings, etc. So to obtain the final distribution, we have to sum over all those scenarios. So this problem has a structure which is very well suited to be implemented in the Monte Carlo code, and this is what is done in the Parton branching method. So before moving forward, I still would like to mention some important features of Parton branching method. So the first one is that it uses the intrinsic transverse momentum. On top of this slide, you can see the initial distribution parameterization, which is used as the input for our TMD evolution. So it contains the collinear part and the Gaussian factor from which the intrinsic transverse momentum is generated. Once we have our initial distribution, we can start our evolution. So our branchings, and in Parton branching, the transverse momentum is calculated at each branching. So here you can see the schematic picture of the branching and the transverse momentum of Parton A, which propagates towards the hard scattering, is calculated as the transverse momentum of the previous Parton minus the transverse momentum of the emitted part. After all the branchings, the final transverse momentum is the sum of the intrinsic transverse momentum and all the transverse momenta which were emitted in the evolution process. Another important feature of the Parton branching is that it implements the angular ordering condition, and it does it in the way similar to Catani-Marchesini-Weber. It means that the angles of the emitted partons increase from the hadron side towards the hard scattering. It allows us to build a relation between the de Graaff evolution scale and the transverse momentum of the emitted parton, to define the scale of alpha S, to define which branchings are resolvable and which are non-resolvable. But what is the most important is that by using angular ordering, we include the soft gluon resummation. So in other words, the leading log and next to leading log coefficients in Parton branching Sudakov form factor are the same as in CSS method. At next to leading log, there is a difference which comes from the normalization group. So this difference is proportional to beta zero function. Another feature of the Parton branching TMDs is that we can take them and integrate them over the transverse momentum, and then we obtain the collinear PDF, which can be used in collinear physics applications. Last but not least, the collinear part of the initial distribution is obtained from feeds to Hera DAS data using XFitter package. So this was the brief description. How do we obtain TMDs? And now we can use those TMDs as the input in TMD Monte Carlo generator, Cascade, to obtain predictions. So Cascade does several things, but first of all, it deals with matrix element. So it can be used in two modes, with off-shell, KT-dependent matrix elements, or matrix elements which are obtained from standard automated methods which are used in collinear physics like PYTHIA or MCA-NLO. This, however, requires some extra effort because we have to convert this collinear matrix element into KT-dependent one by adding the transverse momentum to our event record according to the TMD. For exclusive observables, Cascade provides the TMD Parton shower, and then we can also use the final state radiation and hadronization via PYTHIA plugins. What is important for my talk, so for Drell-Yan PT spectrum in the low and middle PT range, is the treatment of matrix element and TMDs. So the method for that was developed already quite a long time ago by PYTHIA authors. So first we generate the matrix element from PYTHIA, so it does not contain, the incoming partons do not contain any transverse momentum. Then we have to add the KT, so to generate KT according to our TMDs. We do it by keeping the mass of the Drell-Yan system fixed, and we still have to change into X1 and X2. And to show you that this works, this is the prediction obtained this way for Drell-Yan PT at 8 TeV atlas measurement compared with the data, and the spectrum is very nicely described. The question was if this method can be used at next to leading order. And yes, but there is some extra effort needed to avoid possible double counting. So what we did we decided to use the Parton branching method with MCA-NLO. In standard MCA-NLO, when matrix element is to be matched with Parton shower, subtraction terms for soft and collinear contributions must be used to avoid possible double counting. And the exact form of this subtraction depends on the Parton shower algorithm to be used. Since the Parton branching TMDs have similar role to Parton shower, the subtraction term has to be also used in our calculation when we want to combine TMDs with NLO cross-section. I mentioned that the Parton branching method uses the angular ordering, and this angular ordering is actually similar to Herwig 6. So what we decided to use is MCA-NLO with Herwig 6 subtraction terms. In this picture, you can see the prediction for Drell-Yan at 13 TeV. And in red, you can see the MCA-NLO calculation with the subtraction term. And in blue, what happens when we add to the matrix element to the event record the transverse momentum according to our Parton branching TMD with the method which I described on the previous slide. So this is the idea. And now we can look how it compares with the data. So this method was first applied to LHC measurement. So here you can see in both plots in red the prediction, which is obtained with Parton branching TMDs with MC and NLO. And on the left compared with 8 TeV atlas measurement, on the right with 13 TeV CMS measurement. And what we can see on both plots is that the low and middle PT spectrum is very well described, up to, let's say, 50 GeV. And what is missing at higher PT is the contribution from Z plus more jets. So what we can do is to have a look at the lower energy, so at Tevatron data. So here there is a Z boson PT measurements from Tevatron, and again low and middle PT range spectrum is nicely described by our method. Then we can go to even lower energies to fixed target and low energy colliders. So here there are 3 plots which come from 3 different experiments from NUC at center of mass energy 38,8 GeV, R209 and 62 GeV, and Phoenix at 200 GeV. The region at which we look here is where PT is of order of mass of Drell-Yan. And again, we see that the PT spectrum is nicely described by MC and NLO combined with our Parton branching TMDs. What is really important here is that there is no additional tuning or adjusting of the method compared to the procedure which we applied to LHC or Tevatron data. So it means that we obtain good theoretical description of the Drell-Yan data which come from experiments in very different kinematic ranges. To understand a bit why it's like that, it's very useful to look at the subtraction terms at different energies. So again, here in red, you can see the MC and NLO calculation with the subtraction terms. And in blue, what happens when we add the transverse momentum to the event record according to our Parton branching TMD distribution. There are 4 plots for 4 different center of mass energies, which correspond to the energies for the experiments which I showed you on the previous slide. And what we can learn from this plot is that at low mass and low energies, even in this region where PT is of order of mass of Drell-Yan, the contribution from soft gluons, so the one which is included in our Parton branching TMDs, is really essential to describe the data. And this changes with the energy. So when we go to LHC energy, and we look at the region where PT is of order of mass of Z boson, we see that here the contribution from soft gluons is small and the spectrum is basically driven by the real hard emission. So the last remark which I want to make before I conclude is about the intrinsic transverse momentum. So this is the initial distribution used in Parton branching method, which I mentioned a few slides ago. So this is the collinear part, which is fitted to the HERA data. And this is the Gaussian factor from which we generate the intrinsic transverse momentum. So the sigma, so the width of the Gauss, is defined as the QS squared over 2. And actually this parameter is not constrained by the current fit procedure. It was just assumed to be half GeV. However, the low mass Drell-Yan data can be used to constrain the intrinsic transverse momentum. So here what you can see is the plot for the chi-squared, so the quality of the fit versus the QS parameter, so the one which constrains the width of the Gauss. And we see that the experiments from data from NUC and R209, they show some sensitivity to this parameter. And there is some minimum for this value, which is actually quite close to the value which was used just by assumption in Parton branching. But we hope that with this, we could constrain this value even better. So to finalize, it was noted in the literature that perturbative fixed order calculations in collinear factorization are not able to describe the Drell-Yan PT spectra at fixed target experiments in the region where PT is of order of mass of Drell-Yan. So our observation is consistent with this remark. We noticed that in this region, the contribution from soft gluon radiation, which is included in our Parton branching TMDs, is really essential to describe the data. The situation is different at LHC, where in the region where PT is of order of mass of Z boson, The collinear calculation gives already good result. Since Drell-Yan PT spectrum is sensitive to both fixed order calculation and soft gluon resummation, the theoretical prediction has to have both elements to describe the data, and the accuracy of the prediction depends on matching between those two. So in Parton branching, we use the matching in the spirit of MC and NLO method. So we do not have additive matching as, for example, in CSS, but we would rather call it operatorial matching. So the Parton branching TMDs act as the operator of unsubtracted MC and NLO cross-section. So yeah, the Parton branching method contains the intrinsic transverse momentum and well-defined perturbative evolution. It contains soft gluon, angular ordered soft gluon radiation, and is matched through MC and NLO method to next to leading order hard scattering. I hope that I managed to show you that this method works in a wide kinematic range. Thank you.
Thank you very much, Rola. That's a very nice talk. Any questions? Okay, I don't see yet a hand raised, so I maybe have just a naive question for just my understanding that I don't compared. So this method compared to the Parton shower and the use of the tuning like we can do at the LHC and like low energy data. So the advantage is that you don't need a tune, or I missed something. Okay.
No, that's correct. That so in standard Parton showers, what you have, first of all, the transverse momentum is just generated in the Parton shower procedure, so it's not constrained by any PDF distribution because the PDFs are the collinear PDFs. So in this method, our transverse momentum is already constrained by the TMD. And then the second big difference is that we don't have any free parameters to tune, like in standard Monte Carlo Parton shower programs.
Yeah, I see. Thank you. So I see Aram raised his hand. Please go ahead.
Yeah, I had a quick question on slide 8. Just to understand, well, actually not slide 8, maybe where you were showing the comparison with Atlas and CMS. Yeah, this one for it also is also slide 8.
Yes, it's over.
Yeah. So I just had a quick question. I mean, in terms of matching this prediction, having these predictions also including for Z+1 jet at NLO, essentially one higher order, is this very hard, or it's pretty much possible?
Yes. So what is currently being done is the matching at leading order, but for different Z plus jet multiplicities, for different jet multiplicities. So this is an extension of MLM method to do that, and then you can really describe the spectrum up to really high PT. At next to leading order, it's it's not being done yet.
Okay, thank you, Aram. So I see a question also from Hannes.
Just a short comment to the Z plus jet. It is absolutely correct what Ola said. For the multi-jet merging at NLO, it is not yet done, but of course the Z plus jet NLO calculation can be directly calculated with the Parton branching approach, including Parton shower and the TMD. And similarly also Z plus 2 jet, but only the merging of different multiplicities is not yet done.
Okay, thanks, Hannes.
Okay, so I don't see any more questions. So thank you very much, Ola, for your nice talk. And I think we can, yes, thank you. We can move on to Zhibo. Zhibo, can you please share your slides?
Okay, no problem.
Okay.
Just a moment. Full screen. Okay.
I'm not sure if it's on, if it's me, because okay, I can see now the slides. Yeah.
Oh, okay. Sorry. Okay, so I will start. This talk covers the latest measurements of W and Z boson production in ATLAS experiment. The measurements of W and Z production not only allow to probe the parameters in the standard model electroweak sector, such as W mass and the wake mixing angle, but also allow to check the consistency of the standard model, for example, lepton universality. They allow to probe the perturbative and non-perturbative QCD predictions too. The production of W and Z at the lowest order in QCD is through the quark anti-quark annihilation. Then as the example of W boson shown here, higher order QCD processes contribute to the non-zero PT distribution. Furthermore, the relevant measurements place constraints on PDF as well. Two measurements will be presented in this talk: the measurement of W and Z cross-section at 2.76 TeV, and the measurement of ZPT at 13 TeV. The decay channels in this talk are limited to electron and muon. Here are the topologies for W and Z events. W decays to one lepton and a neutrino. The missing PT of the neutrino is measured through its relation to lepton PT and a hadronic recoil UT, where recoil is the vector sum of all topo clusters, excluding those from leptons. As an important observable, W transverse mass MT is measured by combining the information of lepton PT, missing ET, and the corresponding phi angles. For Z decay, both leptons are detected, giving an invariant mass peaked around the Z mass. These are the W and Z production cross-sections by various experiments and by the corresponding predictions. The blue curves stand for the predictions of proton-antiproton collisions. The black, green, and brown ones represent the predictions in proton-proton collisions. And the latest measurements by ATLAS at 2.76 TeV, indicated by the red dashed circles, will be covered in this talk. So let's start with the measurement of W and Z production cross-section. The data of this measurement is collected in February 2013 from proton beams at LHC at 2.76 TeV. The integrated luminosity is for inverse picoband with an average pile-up of 0.3. In Monte Carlo simulation, the signal samples are generated by Pohag box plus PyTR8 at NLO. Electron is reconstructed by clusters of energy in EM calorimeter and matched to track in inner detector. The fiducial cuts for electron require PD higher than 20 GeV, eta lower than 2.4, skipping the transition region between barrel and end cap calorimeters. Muon is reconstructed by combining the tracks in the muon spectrometer, and in the inner detector, it is required to have PT larger than 20 GeV and eta below 2.4. W event selection further requires missing ET higher than 25 GeV and MT higher than 40 GeV. In Z selection, the invariant mass of lepton pair is between 66 and 116 GeV. Here is the summary of observed candidates and the estimated background in each channel. The background fractions in Z channels are much lower than those in W channels. Then the spectra of MT and MLL are also presented, showing both data and predictions. In background estimation, the electroweak contribution and top quark related processes are estimated by simulation, while multijet in W is derived from data, as illustrated in the next slide. The multijet templates in electron channels are missing ET spectra in control region, where the electron identification is reverted and the missing ET cut is removed. The templates in muon channels are empty spectra in control region, where the muon isolation is reverted and the empty cut has been removed. Then the shape of multijet is extracted from the template in the control region, excluding contributions of signal and other background. The normalization of multijet in signal region is achieved by a chi-square fit of template to the sum of all the components. On the right, we have the distributions that are used to estimate the multi-jet contributions in electron and muon channels. The overall number of multi-jet background is estimated from the fit to the total W boson sample. The fiducial production cross-section is calculated by dividing the number of signal events by the integrated luminosity corrected for the detection efficiency. The value of this efficiency depends on the channel. The total production cross-section in each channel is extrapolated from the fiducial cross-section with correction of acceptance. The central values of acceptance around 0.6 are determined from MC samples. As shown in the table, muon trigger as well as electron reconstruction and identification uncertainties are the dominant systematics in the efficiency factor. The acceptance factor has an uncertainty that ranges from 1 to 1.4%, depending on the channel due to the choice of PDF set. The choice of event generator and Parton shower models also result in an uncertainty of 0.9% on the acceptance. Here are the fiducial cross-sections of W plus, minus, W combined, and Z. The green arrow bands represent the total uncertainty of the measurement. The points with arrow bars are given by theoretical predictions of different PDF. The agreement here is good in general. The ratios of cross-sections benefit from the cancellation of systematics. The test of lepton universality is presented on this page based on the ratio of fiducial production cross-sections of electron channel over muon channel for W and Z. The constraints between RW and RZ are presented on the right. The result of this measurement is indicated by the green solid line. The empty circle marker in the center represents the standard model expectation in this plot. The ratios of fiducial production cross-sections of W over Z and W plus over minus put constraints on distributions of strange quark and valence quarks respectively. The comparison of data to predictions are placed on the right, where you can see the measurements are dominated by statistical uncertainties in yellow. In other measurements at higher energies, the statistical uncertainty is much smaller thanks to the larger data set. The ratio of W plus over minus is commonly expressed in the form of charge asymmetry in W boson production, which also benefits from the cancellation of systematic uncertainties. The next publication is on the measurements of ZPT at 13 TeV. The distributions of two observables are measured in this work, specifically the transverse momentum of the dilepton pair, as well as phi eta star. A precise measurement of PTLL is important for both beyond standard model searches and standard model precision measurement. The phi eta star is defined in the way such that it depends exclusively on the directions of the leptons. This overcomes the limitations of lepton momentum resolution in low PTLL regime. The analysis uses the data collected in the combined 2015 and 2016 proton-proton collision at 13 TeV with an integrated luminosity of 36 inverse femtobarn. The plot here shows the pile-up in this period, indicating the different average pile-ups in 2015 and 2016. The MC signals are simulated by Paul box plus Pythia 8. The electron candidate is reconstructed by clusters of energy in EM calorimeter matched to ID tracks. The fiducial cuts for electron include PT higher than 27 GeV, eta lower than 2.47, excluding the transition region. The muon candidate is reconstructed by combining the tracks in the muon spectrometer and the inner detector. The PT of muon is to be higher than 27 GeV. The eta is within 2.5. In addition, the selection of Z requires two leptons with invariant mass between 66 and 116 GeV. The number of events and estimated background components are listed in this table. The fraction of background is less than 1% in both EE and mu channels. The spectra of the two observables in electron channel are put on the right, together with the comparison of data to predictions. Disagreement in the tail is expected because the generator is effectively a computation at leading order in alpha S in this region. The fiducial cross-sections are the number of signal events divided by luminosity and corrected for detection efficiency. Final differential distributions use Bayesian unfolding to account for the detector effects. The response metrics and the correction for reconstruction efficiency are derived from signal MC samples. The systematic uncertainty in detection efficiency factors is dominated by lepton identification and reconstruction efficiencies, while theory and modeling uncertainties are negligible. For the spectra of observables, PTLL and phi eta star, the systematics in normalized differential cross-section is shown on the right for electron channel. There is a division of linear and log scales on PTLL distribution at 30 GeV. The measured fiducial cross-sections in individual channel and after combination are presented. The prediction made at NLO in alpha S using CT14 PDF set is comparable to the combined cross-section within uncertainties. The measured normalized cross-section from PTLL and phi eta star are presented on the right. The poor distribution defined as the difference between EE and mu channels divided by the combined uncorrelated uncertainty is also shown in the bottom panel of each plot. The bond level combined measurements of normalized distributions are compared to different predictions. Among the 4 predictions, the reddish program combines a fixed order prediction of Z plus jet with resummation of MLL over PTLL terms. The green curves here stand for the reddish prediction, except for larger uncertainties in the low PTLL and low phi eta star regions. It agrees with the data over the spectra with uncertainties typically from 1 to 3%. To summarize, the production cross-sections for W and Z are measured using Atlas data at 2.76 TeV in fiducial region and extrapolated to the full phase space. Measured ratios and asymmetries are also reported in agreement with NLO QCD calculations. PT and phi eta star spectra of Drell-Yan lepton pairs have been measured by Atlas at 13 TeV. The data agrees with QCD prediction based on resummation approaches within uncertainties. Thank you for your attention.
Okay, thank you very much, Zhibo, for your nice talk. I see Artur has a question. Please go ahead.
Oh, yes. Thank you, Zhibo. Can you please go to the page 4? I have a question concerning the cross-sections which we have at different center of mass energy published in Atlas, which you showed at page 4, I believe.
Okay, I think we are on page 4 now.
Oh, okay. Yeah, you showed here the published results for cross-section for 7, 8, and 13 TeV, and also in Atlas we have ratios of the cross-sections between all the 3 centers of mass energies, and also you showed same measurements at 2.76 TeV. And my question would be, are we going in Atlas to have measurement of the grand ratio where we have all 4 centers of mass energies, 13, 8, and 7, and 2.76 cross-section ratio, which will gain in precision from one hand side, but from other hand side for 2.76, as you showed, we are dominated by statistical uncertainty. But yeah, do you know anything about the plans regarding such type of measurements?
Sorry, maybe again, because yeah. Excuse me, because I didn't fully get your idea. What was your question exactly, please?
Yes, sorry, probably I was not clear. My question is, are we going to make measurements of the ratios between 13.87 and 2.76 for W and Z?
The ratios? Okay, is it something related to this ratio?
Yeah, sorry. So we have published ratio for 13/8 and 13/7 cross sections. Yes, and now we have published 276 as you showed. And
yes.
The question is, do you plan to have 4 types of ratio? One ratio of between 4 center of mass energies, 13/8/7/2.76, because as you said, it's very useful to have ratios because we cancel a lot of experimental uncertainty, and it can be used as input for the PDF studies, especially for PDF fits, let's say.
Okay, here I only have these ratios for W/Z and W plus over W minus, and on this page we have the result for 2.76 TeV, and you see the uncertainty is dominated by data statistics, but I also included the result at other center of mass energy. For example, here we have the 2 ratios at 7 TeV and the 2 ratios at 13 TeV.
Yeah, thanks. Okay, thank you.
Okay, thanks.
Okay, thank you. I don't see any more hand raised, so I think we can thank you, Zhibo. Thank you very much for your nice talk. And we can move on to Federico. Federico, can you please share your slides? Yes, we can hear you. I think it's a bit yeah, I can hear some echo, but maybe it's only me.
Because
oh, that's much
now?
better now. Yeah, that's much better.
Okay. Let's try. Okay. Good afternoon, everybody, to who is connected, to whoever is connected to this nice session. I'm here to present 2 measurements of the boson production in association with jets with the Atlas detector. Okay. And okay, first of all, let me just stress in one slide why it's important to have W and Z boson plus jet production measurement at LHC. Okay, as most of you probably know, we have abundant production of W and Z boson plus jet at LHC, and has also a clear signature, so we can use it as a crucial probe of QCD and Electroweak dynamics as this kind of Feynman diagrams that I put here as example want to symbolize. In particular, we can test with this precision measurement the state of the art of fixed order imperturbated QCD predictions, for example, or test the Monte Carlo simulation in various aspects, in particular for what concerns matrix element plus Parton shower simulation. Then, if we look at this kind of process from another point of view, we are sensitive to the aspects of proton Parton density function, so to PDF, and as a process also useful for the rest of the physics that we do in Atlas CMS and in large LHC experiment, we want to know very well this process as a background to other searches, for example, beyond standard model searches, or for Higgs measurement. As you can see, for as an example here, this is the Higgs BB observation, and the dominant and irreducible background comes from Z plus jets. Because of this important landscape that we are looking at. There is a vast set also of measurement that Atlas produced at different square root of S. You can see here an example of the full, well, of a partial set of them. And I will discuss here just two results that are more recent and looking at two different aspects of this investigation that I was mentioning before. There is the double differential Z plus jet cross-section at ATV that gives an important new constraint for PDF fits, and this is the link at the publication. And then there is this result is from 2019, and then there is a result more recent from last year that is the differential Z plus B jet cross-section at 13 TV that is mainly used as a test of Monte Carlo technology, in particular in the form of matrix element plus Parton shower and of the proton structure. And you can see here the publication link. There are also related talks at to V plus jet measurements in general that I will not that discuss other measurements that I will not touch here. There is in particular the Electroweak part covered in Max Gobich's talk, and the interpretation of the PDF constraint, especially from this measurement, the first measurement of the two that I will present, that is discussed in James Ferrando's talk. That there is the link here, and here there were the discussion of other boson without jet and plus jet, for example, for the collinear result from CMS in this session today. So I have these two measurements that are investigating different data sets and offer to us experimental physics different challenges. So let's briefly look at the different characteristics of these two measurements in general. They are both Z plus jet, but the first is at ATV and is using 20 inverse femtometer of data collected during the LHC run 1. And because the aim of this result is to have a better and improved constraint on PDF fits, it was important to use one of the characteristics of the Atlas detector, that is the coverage in the forward region with calorimeter of good quality, because this allows to probe high X values in the PDF extraction. So it's important to look also in this very forward region of the Atlas detector with calorimeters. For Z plus B jet, this is a measurement done at 13 TV with the 36 inch femtometer of data collected in the first part of run 2 LHC, and it was say a big improvement in the Atlas detector, the installation of a new pixel layer very close to the beam pipe that basically you can see here in the picture that allows a better identification of secondary vertex decay at the distance of the order of a few hundred microns that are the signature of the heavy flavor decay inside the BGF. So it's important for the identification of the final state, and this was an important detector upgrade of Atlas that is relevant for this measurement. So let's start with the Z plus inclusive jet at ATV to explain the selection that is a reasonably standard selection for signal candidates. And in general, in run 1, we selected the leptonic decay candidates very efficiently because we could use low PT cuts because the low threshold in lepton selection at online and offline level because the environment was a bit cleaner, and there was a wide cut around the Z mass window of plus or minus 25 GV in the lepton invariant mass. About the jet reconstruction, we are using here the standard in Atlas anti-KT clustering argument with a delta R parameter of 0.4, and the selection is inclusive because we require always at least one jet in the event with up to a high rapidity, as you can see from this rapidity range up to 3.4, because we want to probe the IX region. In the high rapidity region, there is also considerable quantity of pileup that cannot be suppressed with the usual techniques that we have in Atlas using tracking information and association to primary vertex. So in this analysis, we were forced to raise the PT cut in the forward region to 50 GV exactly to avoid contamination from this source of background. The rest of the background is almost negligible, as you can see from this plot of one slice of PT versus the rapidity of the jets. And it was estimated with a combination of Monte Carlo and data-driven techniques. So after this, the goal of this analysis is to obtain a double differential cross-section in PT of the jet and rapidity of the jet. And to do that, to have, in particular with this double differential cross-section, we obtain a very strong constraint on the PDF fits. And to obtain that, we need to extract the number of this NIP, this number of jets in data at particle level after the background subtraction. So we built the migration matrix, that two-dimensional migration matrix using Monte Carlo to estimate detector efficiency and resolution effects. And you can see the example of this nice two-dimensional matrix here. Basically on the diagonal, you have the eta, the rapidity migration, and the 5 PT beams are identified by sub squares inside this big migration matrix. After that, we can use a iterative, quite standard techniques at the moment of iterative Bayesian unfolding to obtain particle level quantities and to compare with the predictions. In run 1, we had several leading order plus Parton matrix element, so Monte Carlo prediction with the leading order in the matrix element plus Parton shower, for example, Argent and Pizia, plus Pizia 6 and Sherpa. And then we were able to compare also to next leading order prediction from Sherpa 2.2 still at using Monte Carlo. For this analysis, it was important also to compare with the fixed order, next leading order, fixed order, next leading order predictions with different PDF models that you can see in the right plot here on the slide. Overall, there is good agreement within the uncertainties that are dominated by the jet energy scale and the statistics at very high PT of the jets. But it's clear that there are some trends that are indeed what we want to use to constrain improved PDF models. So next analysis that I will present is the Z plus B jet at 13 TeV. The Z selection is quite standard, just we have to rely on slightly higher PT cuts on the lepton selection. And the big difference here is coming from the B jet, so from the flavor identification of the jet candidates in the event. Here we have to rely on the long lifetime, the presence of secondary vertex, and the decay pattern of heavy flavor hadrons. So these are all tracking information that result in difference in the track pattern of within the jet, and all this information is condensed in a multivariate algorithm that allows us to separate with one single score B jets with respect to the other flavors, so C and light. And you can see the discriminating variable that we use for the flavor tagging, for the B tagging, in this plot on the right. In general, we apply for the selection of B jets a cut in this variable that select B jets with an efficiency of 70%. This is our B tagging working point selection. With this 70% selection for B jets, we have a contamination not negligible from C jets also of 10% and small but still not negligible of below 1% from light jets. So you can see here some of the challenges of this analysis with respect to the previous one. First of all, as I said, the non-B jet background is sizable and as an additional problem is also affected by large uncertainty. So there was a more complex approach for the background estimate, and it was done in a data-driven way using a template fit of this multivariate discriminant. binned according to this bitagging efficiency cut. You can see here an example of these 3 bins that were used to fit different templates of C and light and clearly of the B. And the bins have different purity, and each of the bins is specifically calibrated using a controlled sample, the efficiency of each flavor. For the 2B jet case, that is the other signal region of this analysis, there was more flexibility because we can combine the score of the B tag discriminant of the 2 jets, and you can see here the example of this template fit also in that region. So after that, the procedure is similar to the Z plus jet inclusive analysis at ATV. So we continue with the background subtraction, and then we bring the data at particle level through the procedure of unfolding, correcting for efficiency and detector resolution effects. You can see the migration matrix here, an example one for the leading V-jet, and you see it's slightly off diagonal because we lose a little bit of energy in neutrino decay and muons that are not added in the jet energy scale. And you can see the dominant systematics still on leading V-jet PT on the right, and the dominant systematics are coming from the background in the dotted violet line, the background subtraction, and the bitagging efficiency calibration that is data-driven, that is also this purple line, but the continuous one. So after this, we can compare with theoretical prediction, and here we want to challenge various aspects of Monte Carlo machinery in the form of matrix element plus Parton shower, and in particular something that is relevant is the choice of the flavor scheme of this simulation, of these calculations. There is a long-standing debate if it's better to use for the analysis and for the simulation of this final state, if it's better to use the 4-flavor scheme that allow an easy use of B quark mass in the matrix element, or the 5-flavor scheme that allows the resummation of large logarithm inside the PDF of the proton, and somehow it allows more leading order diagrams that you can see here, for example, on the left. This is allowed in the 5-flavor scheme at leading order. On top of that, we checked many other aspects of our Monte Carlo simulations. We checked different accuracy at the level of matrix element, leading order, next leading order, different number of partons, and then various approach for the Parton shower, looking in particular at Alpgen, Sherpa, Impizia, or the Sherpa. Parton shower. And this is the summary of all these different predictions that we tested, so a total of 8 different predictions. So the results, if we compare with the measured data in the 1 tag region, so in the Z plus 1 or more B-jet here on the left, and Z plus or more with 2 or more B-jet on the right here, and you can see that in the 1 B-jet case, there is a set of points that is off with respect to the data measurement, and these are all coming from 4-flavor scheme predictions, both at leading order, next leading order. So I would say that that 5-flavor scheme prediction are matching our data both in 1 B-jet case and the 2 B-jet case, although, for example, the 2 B-jet case, we have still very large experimental uncertainties, a measurement totally dominated by systematic uncertainties, and it's hard to disentangle if one approach is better than the other. Then, if we want to learn something more, we can look at the differential cross-section measurement that are available on the paper. There are many available differential distribution. And in particular, you can see on the left an angular distribution, the 1B jet case, where there are some deficits, let's say, especially in the, and also some trends in the 4-flavor scheme predictions. And the other interesting distribution that I put here, there are more in backup, is the MBB in the 2B jet case, where there are some tensions in the very high high MBB region. these tensions are covered somehow by the large uncertainties in the predictions, and also we have some large uncertainty in the data in this region. So somehow we can conclude that this region is challenging both for the prediction and for the experimental aspects. So this can be something to keep in mind for searches or for the study of other processes in that region. So basically, let me to conclude, I presented these two results, the double differential Z plus jet measurement at 8 dB and the differential cross-section Z plus B jet measurement at 13 dB. These are showing different aspects of the importance of V plus jet measurement at LHC, mainly related to the understanding of QCD theory, PDFs, the Monte Carlo technology, and in general for the advancement of the various aspects of the experimental physics at LHC. In future, we will use larger statistics, but the key point is that we need to improve the V plus jet measurement themselves, reducing systematic uncertainties to obtain a better measurement and compare in a better way to predictions. So stay tuned, these measurements are ongoing. Thanks a lot.
Thank you very much, Federico. That's a very clear talk. Any questions? Okay, I don't see yet her hand raised. So maybe just a quick question. Oh, sorry. Maybe, okay, Robert, can you please go on? I will go afterward.
Yes, I was just wanting to ask, we actually fit ZPT data at 8 TeV. I just wanted to get your understanding of how independent the two data sets are, or would you need the statistical correlations in order to fit them simultaneously?
I think that so there are several aspects. So I would say that this measurement is dominated by jet energy scale uncertainty. So the main systematic is, I have the systematic in backup, is uncorrelated between the two measurements. So you can see here, we are really far away. So the dominant is really jet energy scale. But, and then there is a set of events that will be common between the two data sets. And that part would need the correlation matrix, the statistical correlation between the two measurements that I don't think is available. So to answer directly to your question, I think the main systematic uncertainty can be taken as uncorrelated, but the statistical part has some partial correlation that is not easy to disentangle.
Okay.
Okay, I see another question from Andre.
Hello, thank you for a very nice talk. I was just wondering about the 4 versus 5 flavor scheme and how does that affect, in a way, how do you interpret theoretical predictions given that there's a difference between these schemes? Does that render theoretical predictions unusable where they are different, or maybe do you tend to utilize one flavor scheme over another because one is, I don't know, maybe assumed more accurate? So what do you have to say about this?
This is a very good point. So one of the goals of this analysis was to understand which is the most appropriate set of setup for a Monte Carlo generator, matrix element plus particle shower, to be used also as a background simulation for other measurement. And I think the bottom line is that we need a 5 flavor scheme prediction in Atlas, let's say, because it's usable in both final state, in the 1B and 2B cases. If, so this is, let's say, one general take-home message from this measurement, that in the final state, in the phase space, with the jets above 20 GeV and so on, up to very high energy of the jets, the 5-flavor scheme are more usable than the 4-flavor scheme. If we look at the details of the prediction, maybe the 2B jet only final state in some parts of the phase space maybe better modeled, or at least at in the same good way modeled as with the 5-flavor scheme. But we are not able to distinguish that. There are some theoretical assumptions about the 5-flavor scheme that the use of the mass of the B in the gluon splitting should produce better results, so more in agreement with data, but we cannot see that yet. And with this level of precision, 5-flavor scheme is just better. If we go in some corners of the phase space, maybe we will be sensitive to the pros and the good side of the 4-flavor scheme.
And does that also extend to W plus jet? What do you think?
For W plus jet, probably the difference is between the two schemes is smaller, because in principle this diagram here is present only for Z production. So the difference between the scheme is for sure larger in the Z case, and you can see in the angular variables this is really striking, as there are trends in these Z plus 1B jet angular variables that are not present in the 5-flavor scheme. For W, I think we can already state that if we look at this phase space with jets beyond 20 GeV, 2B jet, and so on, the 5-flavor scheme should not be bad, should be good enough, let's say. If we want to investigate finer details, this analysis is not yet precise enough.
Okay, thank you very much.
Welcome.
Okay, so I will leave my question offline to you, Federico, so because we need to move on. So thank you very much for your nice talk.
Welcome. Thanks to you.
Thank you. We will move on for the last talk of our session today. So Juri.
Hi, you can see me and hear me? Hello?
Hi, yes, I can hear you, yes.
Okay, great. Let me share my slides. Can you also see the slides?
Not yet for me.
Yeah, you can see.
Oh, yeah, okay, thank you.
Okay,
yes.
I'll just a bit of delay. All right, thank you for the opportunity of presenting this talk. The subject of this presentation will be, we will show some results on the impact of Drell-Yan data, in particular the charged and neutral asymmetries on PDF determination. This is an overview of the talk. I will just stress briefly the potential of Drell-Yan data in PDF determination. I will show the results of the profiling that we obtaining, including W asymmetry pseudo data, and show its complementarity with the neutral channel asymmetry, forward backward asymmetry. And then I will move on to some application of this new profiled PDF with the reduced PDF uncertainty, about the recent results on the proton antimatter asymmetry, possible application on the determination of W mass, and some BSM searches in neutral and charged channels. So we have seen in the been stressed very explicitly in the previous talks the importance of Drell-Yan data in the determination of PDFs. These Drell-Yan data indeed has now a very has been measured very precisely, and it features low theoretical and experimental systematics, and thanks to the high statistical precisions and the good control of the correlation, it can be successfully employed in PDF fits. This work that I'm going to present, it follows a list of previous works that we have done with the same spirit. We have first included forward-backward asymmetry in the study of profiled PDFs in this paper here, and earlier today, Simone Amoroso has presented another recent study that we have done for the profiling of PDF employing the A0 coefficient in the expanded Drell-Yan cross-section. And in this talk, instead, I will focus on the potential of Lepton-Charge asymmetry, AW, and its complementarity with respect to the forward-backward asymmetry. So just as introduction, this is the observable that we are going to discuss, is defined as the normalized difference between the W plus and W minus cross section. As a first step of our analysis, we have calculated these observables at next to leading order accuracy, and we have also supplemented a next to leading order QCD K factor in order to have the best accuracy possible. As a first check, we have tried to fit to compare this data to our prediction to the experimental data, and we have obtained a very good description of the experimental data using various PDF sets. The following analysis that I will present has been done employing the public code XFitter, which has been used for the profiling of the PDFs. And we have studied the impact of pseudo data with a center of mass energy of 13 TeV, projecting its statistical precision for these two integrated luminosity of 300 inverse femtobarn, so for the statistics at the end of LHC run 3, and 3000 inverse femtobarn, which would be the integrated luminosity at the end of the high luminosity stage. Then I will move to showing you the results of the profiling that we have done the studies using employing the CT18 and NLO PDF set. The two plots on the top show the distribution of U valence and D valence Quark PDFs, where on top of the baseline CT18 and NLO PDF sets, we have imposed constraints from forward-backward asymmetry at two different integrated luminosities at 300 and 3000 inverse femtobarn. While in the bottom, we have the same results, where instead of forward-backward asymmetry, we have employed the AW asymmetry. It is visible that we are able to reduce the error, the uncertainty PDF error bands on the U valence and D valence Quark, with AFB being slightly providing slightly stronger constraints on the valence Quark. And it's also important to stress that we observe some saturation effects between the impact of the data at 300 inverse femtobarn and at 3000 inverse femtobarn. So the reduction of uncertainty between the two projected statistic is small. If we have a look at the anti-Quark PDFs, we observe instead that the AW provides slightly stronger constraints than the forward-backward asymmetry. And in particular, this happens for U-bar PDFs in the low X region, so yeah, around here, and for D-bar in the low and intermediate X region. So in these kinematical regions, the AW seems to bring a slightly better constraints than forward backward asymmetry. But what is mostly important is the results that we have on the combination of the two observables. Here in these plots, we're reporting the reduction of uncertainty from the combination of the two observables. Here in the first row, we have the U valence, D valence, and the combination D valence minus U valence PDFs. And especially in the last one, which is the combination that is most sensitive, we have checked that this is the most sensitive combination on AW data. We can observe a very large reduction of the uncertainty, especially in the low X and intermediate X regions. You can see indeed also that we can improve from the imposition of the forward backward asymmetry only to the forward backward asymmetry and AW. On the bottom, we have the results instead for the anti-Quark PDFs. Again, we observe a quite large reduction of uncertainty in the intermediate, low, intermediate, and also we have quite strong effect also in the high X region. Similar saturation effects is visible, although it's not here shown, the 3000 inverse femtobar, but the reduction of uncertainty again is not too large, going from 300 to 3000 inverse femtobar. So I move on to the application of some of these results. The first would be to show which would be the impact on the PDF's error in the ratio of D bar over U bar. Here it is shown with two, in the left you have 300 inverse femtobar and on the right of 3000 inverse femtobar. We are focusing now in the high X region, and just as a comparison, we have superimposed the recent sequenced results. This is just to show that in this case is the AW observable has a very large impact on this particular combination of PDFs in this high X region. Yeah. Possibly this data will move the central value of these curves, but the reduction of the uncertainty is remarkable. Another application that this profile PDF would have is in the determination of the W mass. The extraction of the W mass is done using mainly there are two possibilities, either looking at the transverse mass of in the Drell-Yan charge, the channel, or in the PT of the lepton. The two are provide a similar sensitivity on this observable. And what we show here is the reduction of the PDF uncertainty when employing the different sets of data. So this blue curve represents the inclusion of the forward backward asymmetry, and in the transverse mass spectrum, the PDF uncertainty will be reduced by about 12% using 300 inverse femtobar data and 16% using 3000 inverse femtobar data. Including instead the AW asymmetry, this reduction of the uncertainty can be further reduced by going down to 26% or 43% by using either 300 or 3000 inverse femtobar. And a combination of the two observables would reduce instead the PDF uncertainty by 28% or 46%, which is this is even at first it seems a very large and good reduction of the PDF. I have to stress that for the extraction of MW, more than the actual distribution in the transverse mass, what is important is the normalized distribution. And in this case, we have observed that the reduction of uncertainty is actually far more moderate, but still worth to be noticed. For what concerns, move to BSM searches, which are done in the high invariant mass or transverse mass region. And I'm showing here the relative PDF error on the cross section. This case is for the dilepton high invariant mass, so for the searches in the neutral channel, important for Z prime searches, for example. And this black curve represents the PDF uncertainty on the baseline PDF sets, and the other curves, again, similarly to before, are the relative error after the inclusion of certain set of pseudo data. And if we take, for example, the PDF uncertainties at 4 TeV, which would be of about 12%, we can reduce by down to 11% or 10.2% with AFB data at these two integrated luminosity. AW data would reduce this uncertainty down to 9.6% and 9.4%. And the combination of the two would instead reduce the uncertainty down to 8.4% or 7.8% at the two integrated luminosity. So a reduction of about 3–4% on the uncertainty. Similar results can be drawn in the high transverse mass spectrum. Here, for example, at 4 TeV, the original PDF uncertainty from CT18 and NLO is 12.9% and can be reduced by a few percent with AFB. Other smaller reduction can be obtained instead from AW data, and the combination of the two can reduce by a few percent the uncertainty in this region. So these results can be relevant for BSM searches. It was stressed also earlier today by Sally Dawson in her talk that we have not found bump showing striking evidences of BSM peak resonance, right? So no Bright-Wigner peak has been observed in the dilepton or transverse mass distribution. So one possibility instead would be to observe the presence of BSM physics in the tails of the distribution. This is what we have done here. We have considered a specific model, an SSM model. Z prime. So basically, we have just added an SU2 symmetry group to the standard model, but with his gauge coupling is now enhanced by a factor 3. So the result is that we are obtaining very broad resonances, as you can see here. For a Z prime mass of 7.2 GeV, we observe this very broad peak, which is not visible due to the large statistical uncertainty. But what could be visible is its effects on the tail of the distribution. So around this region here, which is zoomed in this plot in the bottom. So here, the evidence for BSM physics would translate into a deficit of events, a depletion of events with respect to the standard model prediction. And if we treat this depletion of events the same as we would do with an excess, we would observe a significance of this kind, which can be reduced by employing these profiled PDF sets using AFB and AW data. So the significance of the signal can rise sensibly, and we can obtain an early evidence of BSM physics by using these profiled PDFs. A similar result we have obtained in the searches for W primes. Here we have chosen a similar resonance, so in the same model with a W resonance of about 10 TeV, and we are exploiting the same effect of the tail of the distribution in the lower transverse mass region that is zoomed here. And again, the reduction of the PDF uncertainty can significantly increase the significance of the signal, leading to an early evidence of BSM physics. So I move then to the conclusions. As we here we have extended our previous works on PDFs constrained from Drell-Yan measurements, which are very important and have a remarkable constraining power on PDFs. We have emphasized that we can the complementarity between the asymmetries in the charged and neutral channels, showing the constraints on valence quarks and on anti-quarks PDFs, and the combination of the two asymmetries. We have shown also some application of the profile PDF with reduced PDF uncertainty, and this is which would be important both for standard model precision measurements, determination of W mass or antimatter asymmetry in the proton, and also for BSM searches, particularly for non-resonance objects in both neutral and charged channels. Thank you.
Okay, thank you very much, Juri. Very nice talk and very nice results. So any question? Okay, I don't see any yet. So maybe I just have a small question, if possible, on your slide 11 for the W mass. Question, you have mentioned actually that the effect on should be mostly on the normalized distribution. So you mentioned that it's more moderate. Do you have an estimate, or it's not something that you'd like to share?
To be honest, on top of my head, I don't remember exactly the number, but the reduction of uncertainty was much smaller. We're talking about % or less. However, okay, this would be the impact of the reduction of the uncertainty. Then, with the effect that this would have on the determination of NW is much more difficult to predict. We are actually considering the possibility of a more dedicated study on this matter, but it requires quite some effort.
Yeah, that would be great. Okay, thank you very much.
May I add just
Francesco? No, please go ahead.
No, I mean, just let the community know that we are currently considering the possibility of performing like a full determination of the AI coefficient. We not only A4 but also like the A0 and the other Drell-Yan angular coefficient, and then perform a profiling exercise with the PDF, and then try to assess the impact of like MW determination. So we are already in contact with theorists which have already addressed the impact of a reduction of on PDF, systematic uncertainty on PDF on the MW determination, or other important standard model parameters like sin squared theta W. But this is, I mean, we have just started considering this possibility, and this work will come at some point.
Yes, thanks, Francesco, for remarking that we are indeed following this program, and the next step would be profiling using all the expanded Drell-Yan coefficients, and as well as the AW, and see which kind of constraints we can get and its impact on standard model precision observables, such as the MW determination.
I'm sorry, I got disconnected. Sorry, I see Robert has a question.
Yes, with regards to the W, so you're using AW, whereas we would always use the total cross sections and maintain all the correlations, where we would argue that you're guaranteed to do better if you do that, because you can only lose information. So is there any reason why
Yeah, so the reason that we have decided for the asymmetry is that because of being a ratio of cross section, we have a reduction of systematic uncertainty. So in principle, in terms of systematics, it should be better. I cannot say.
Maintain the correlation. If you maintain all the correlations, that shouldn't be true.
Yeah, I mean, I cannot say if this is better or worse than using just the cross section. But this is actually something that we can check. Perhaps, probably, as you said, if one includes also all the correlation, the effect would be comparable.
Well, it's not so much comparable, it's that you actually lose information about the overall normalization, for example, and in particular, the relative normalization of the W and the Z is very important in providing PDF constraints.
Right, yeah.
Just sorry for interrupting you. I mean, here we are not talking about a proper PDF fit. We are talking about profiling, Robert. So actually, we are not considering all the full breakdown of all the systematics information. Here we are just basically considering just statistical uncertainty to perform this profiling when considering pseudo data for the two luminosity scenario here listed by Juri in the slide.
So the argument is that for the PDFs that you're particularly interested in, this is sufficiently good.
Yeah, I mean, right now we are assuming that there are no systematic uncertainties on the data we are using for profiling. So we are just scaling the statistical uncertainty of the carbon determination to the two luminosity scenarios.
Okay, thank you, Francesco. Thank you, Juri. So I don't see any more questions. So thank you very much, Juri, once more for your nice talk. Thank you. And so, yes, that was the last talk of our session today. So we would like to thank all the speakers again. And we thank all the participants for the nice discussion and for staying until the end. So we will close the session today and we will convene tomorrow at 8 a.m. New York time. We hope to see you there tomorrow again. Okay. Thank you very much, everyone. Bye-bye.
Thank you. Bye-bye.
Bye.